Good day. The topic is frictional or skin resistance Q sub S for clayey soil. So the resistance Q sub S is equal to perimeter P times length L times unit friction F. And the three methods are alpha, lambda, and beta method. So for alpha method, the unit skin resistance or F can be represented by F equal to alpha times Cu, where alpha is the empirical adhesion factor, which can be determined using table 3.6, or it is a function of vertical effective stress and undrained cohesion. Thus, alpha is equal to C, that is about 0.4 to 0.5 for board piles, and greater or equal to 0.5 for driven piles. And multiply that to the quantity, sigma O prime bar, which is the average vertical effective stress, divided by C sub U, which is the undrained cohesion, raised to 0.45. So take note that if the values were not available, then we may apply interpolation for table 3.6. So thus, since for this method, if we may now encounter layers with different C sub U value, then the resistance is equal to the sum of P times delta L times F. And it is better to present solution in table form. For lambda method, so proposed by V. Haverhia and Falk, the average skin resistance or FAV can be represented by, so FAV is equal to the lambda times the quantity sigma O prime bar plus 2 times Cu, wherein the sigma O prime bar is the mean effective vertical stress for the entire embedment length. So this is from stress diagram. So prior to the determination of the sigma O prime bar, you need to draw first the stress diagram. Thus, if you have the stress diagram, the sigma O prime bar is equal to A sub 1 plus A sub 2 and so on up to A sub n, wherein A is the area per segment. So divided by the total length of the pile. C sub U, on the other hand, is the mean undrained shear strength. So at phi, that is equal to 0. So for C sub U, it is equal to the sum of the individual C sub U times the individual or sectional length divided by the total length of the pile. And for the lambda, lambda is the function of pile penetration, which is from table 3.7. So take note that L must be in meters. Therefore, if we have length L in feet, we need to convert it to meters, then use table 3.7. So if values are not available, then we may apply interpolation. And for our Q sub S for this method, it is equal to P times L times F ab. So for the last, which is the beta method, so the unit skin resistance or F can be represented by, so F is equal to beta times sigma O prime, and beta is equal to K times tangent of P prime sub R, wherein our sigma O prime is the average vertical effective stress per segment length. P prime sub R is equal to drained friction angle of the remolded clay. K, on the other hand, is the earth pressure coefficient. So conservatively, use K as the at rest condition. So again, for at rest condition, we have two different conditions of the soil. First is the normally consolidated clay, that is K is equal to 1 minus sine of Phi prime sub R, and the overconsolidated clay, that is K equal to 1 minus sine of Phi prime sub R multiply to the root of OCR. So same as the alpha method, we may encounter layers of varying parameters. Thus, the resistance is equal to the sum of the perimeter times the segment length times the unit friction. And it is better to present solution in table form. So for our sample problem, a driven pile in clay is shown in the figure, that is figure 3.37. So the pipe has an outside diameter of 400 millimeters and wall thickness of 6.35 millimeters. So determine Q sub S using letter A, alpha method, letter B, lambda method, and for C, beta method. The top 10 meters of clay is normally consolidated. So this first layer. And the bottom clay layer has an OCR that is equal to 2, which means that it is over consolidated. And for this letter C, which is beta method, use phi prime R equal to 30 degrees. So let's consider alpha method, whose Q sub S is equal to the sum of P times the segment L times F. And F is equal to alpha times Cu. Thus, the resistance is equal to the sum of P times delta L. Then again, F is the alpha times Cu. So for layers, it is better to present solution in table form. Thus, assess first what are the varying parameters in the equation. So first, for P is constant, therefore it is not varying. Why? Because our section is constant with a diameter that is 0.4 meter. Next, delta L and alpha are dependent on the value of our C sub U. Thus, by inspection, C sub U is varying. So, delta L and alpha varies as well. So, in table form, the different processes are to determine the span depth and determine the sectional length with this depth with varying Cu, thus the ratio of our Cu to Pa to determine alpha, then segment Q sub S. So to start, let us consider layers near ground surface. Thus from 0 to 5, depth, the delta L is 5 meters. And C sub U is equal to 25 kilopascals. So for 5 to 10 meters depth, delta L is equal to 5 and C sub U is equal to 40 kilopascals. For 10 to 30, that is with delta L 20 meters and C sub U, which is 90 kilopascals. So knowing C sub U, we may determine the ratio of Cu all over Pa, where Pa for this problem, which is metric, so 100 kilopascals. So, but on the other hand, if that is in English, please consider 2000 PSF. So for the first value, which is Cu 25 all over Pa, that is 100, it is 0.25. For second, it is 40 divided by 100, or that is 0.4. And for third, 90 divided by 100 is 0.9. Next will be to assign values of alpha using table 3.6. So if the reference data is not available, then apply interpolation. So for ratio equal to 0.25, the value is in between 0.2 and 0.3. Thus, apply interpolation. So with interpolation, we have now alpha minus 0.92. So alpha is the unknown, divided by the outer difference, 0.82 minus 0.92, equal to 0.25, our known ratio, minus 0.2, then divided by 0.3 minus 0.2. Therefore, alpha is 0.87. So next, the value is 0.4. So directly from table, alpha is equal to 0.74. So for ratio equal to 0.9, the value is in between 0.8 and 1. Thus, apply interpolation. So for the interpolation, we have the unknown alpha minus 0.54 divided by the outer difference. So 0.48 minus 0.54, do the same for our ratio, that is 0.9 minus 0.8 divided by the outer difference, 1 minus 0.8. Therefore, alpha is equal to 0.51. So for the last phase, we have now the segment QS. So for the individual or segment QS, it is equal to P times delta L times the alpha times CU, wherein the unit is in kilonewtons. So for segment 0 to 5, the QS is equal to pi times 0.4 for our P, so times segment length, that is 5, times the value of alpha, which is 0.87, then times the value of CU, which is 25. The value of the first component is 136.659 kilonewtons. So for segment 5 to 10, so QS is equal to perimeter pi times 0.4 meter times the segment length, which is 5 meters, multiply to the alpha, which is 0.74, times CU of 40 kilonewtons per square meter. The value of the component QS is 185.982 kilonewtons. And for the last segment, which is from 10 to 30, QS is equal to pi times 0.4 for P times the segment length, which is 20 meters, times the value of alpha, 0.51, then times the value of CU, which is 90 kilonewtons per square meter. Thus, for the component QS, it is equal to 1,153.593 kilonewtons. So for the sum now, or the total value of Q sub S, we need to sum all components QS, then QS is equal to 1,476.234 kilonewtons. So for lambda method, whose QS is equal to P times L times F of. And F of is equal to lambda times the quantity sigma O prime bar plus twice of Cu. Thus, the resistance is equal to P times L times lambda times the quantity sigma O prime bar plus twice of Cu. The function of pile penetration, or lambda, for L equal to 30 meters from table 3.7, the value is 0.136. Then, for mean effective vertical stress for the entire embedment length, from stress diagram, so we need to draw the stress diagram. So for the sigma O prime bar, it is equal to A1 plus A2 and so on up to the last area divided by the total length. So for our sigma O prime bar process, first, determine the effective vertical stress or overburden pressure per interface. So again, as a review, our sigma O prime bar, or sigma O prime rather, is equal to the summation of gamma prime times Z, wherein gamma prime is the effective unit weight. That is equal to gamma sat minus gamma of water. So we have 4 different points to consider. First is at Z equal to 0. Therefore, sigma O prime that is at Z equal to 0 is equal to 0 because Z is already 0. So at Z equal to 5 meter, sigma O prime is equal to gamma as 16 multiplied to Z that is 5, which is equal to 80 kilopascals. Next, at Z equal to 10 meters, the sigma O prime is equal to the weight at Z equal to 5, or the weight above. So which is 80 kilopascals plus the effective unit weight for the second segment. That is, we have now our gamma sat 17 minus 0.9 or 9.81 in kilonewtons per cubic meter for water, and multiply this effective unit weight to the remaining depth, which is 5 meters. Thus, our effective stress at this point now is equal to 115.95 kilopascals. Then at the last point, or at the tip of the pile, so Z equal to 30, the sigma O prime is equal to the weight at Z equal to 10. So we pre-identified already up to this specific point, or at Z equal to 10. So which is equal to 115.95 kilopascals. So we will then add the remaining weight, which is equal to the effective unit weight, that is 18 kilonewtons per cubic meter minus the unit weight of water, that is 9.81 kilonewtons per cubic meter. Then multiply it to the remaining depth, which is 20 meters. Thus, the effective stress at that point is 279.75 kilopascals. Second process is to plot the values of effective stress. Again, at the first point, we have 0. At the groundwater table surface, that is 80. So at the interface of the two clay soil, we have 115.95, and at the tip of the pile, which is 279.75, all are in kilopascals. So, and connect using straight lines. Third process is to determine the corresponding area of the stress diagram per layer. So for first segment, so the first area is equal to, so with triangular shape, it is equal to 1/2 times the base of 80 times the height, which is our segment length 5 meters. Or the first area is 200 kilonewtons per meter. So for second segment, we have now the area in trapezoid. So that is equal to 1/2 of base 1, 80, plus base 2, 115.95 in kilonewtons per square meter times the height, which is the segment length 5 meters. Thus, area 2 is equal to 489.875 kilonewtons per meter. And for the last segment, so our area 3, which is in trapezoid again, is equal to 1/2 times base 1, 115.95 plus base 2, 279.75 in kilonewtons per square meter, multiply that to the height, which is the segment length 3, 20 meters. So our next goal is to solve our sigma O prime bar, since we have already the values of our areas. So substitute the different values of our area, particularly A1 is 200, A2 is 489.875, A3 is 3,957, all are in kilonewtons per meter. So divide this to the total length, which is 30 meters. Therefore, sigma O prime bar is equal to 154.896 kilonewtons per square meter. Next, for mean undrained shear strength, or C sub U, it is equal to the sum of the individual C sub U multiplied to the segment length all over the total length of the pile. So substitute the individual CU and corresponding segment length. So for, or starting from the top, we have now CU1, which is 25, multiplied to the segment length, which is 5, plus CU2, that is 40, multiplied to the segment length, that is 5, then plus CU3, that is 90, then multiplied to the segment length, which is 20 meters. So sum all, then divide this to the total length, which is 30 meters. So the value of the mean undrained shear strength is about 70.833 kilonewtons per square meter. Therefore, for QS, QS is P times L times lambda times the quantity sigma O prime bar plus twice of CU. Substitute the parameters for the perimeter. Since this is circle, we have now pi times d of 0.4 times the total length, that is 30 meters, times lambda from our table is 0.136. Then multiply that to the quantity. We have now the value of our sigma O prime bar, that is 154.896 kilopascals, plus twice of CU, that is 70.833. So for our QS, QS is equal to 1,520.499 kilonewtons. So for beta method, with QS equal to the sum of P times delta L times F, where F is equal to beta times sigma O prime, and beta is equal to K times tangent of P prime sub R. Thus, the resistance is equal to the sum of P times the segment length times K times sigma O prime, then times the P prime sub R. So for layers of soil, it is better to present solution in table form, similar to alpha method. And assess first what are the varying parameters in the equation. So for us to limit our solution in table form. So starting with perimeter P. So perimeter P is constant, therefore it is not varying. So from the top till the tip, the section is circle with diameter that is 0.4 meter. Next, delta L is dependent to sigma O prime. So next to delta L is K. So K is varying because the first 10 meters, according to the problem, so first 10 meters from ground surface is normally consolidated, while the remaining is over-consolidated with an OCR value of 2. And next will be the sigma O prime. Sigma O prime is indeed varying due to the presence of the different unit weight. So we have 16. We have saturated unit weights, so 17 and 18. due to the presence of groundwater table. Thus, if sigma O prime is not constant, then delta L, or the segment length, must be considered as varying as well. And last, the angle inside the tangent function is constant for this problem with a value that is 30 degrees. So in table form, the different processes are to determine first the segment depth, next is the segment length as per depth, next the coefficient k accordingly, and the average sigma O prime. And finally, the value of the frictional resistance Q sub S. So to start, let us consider layers near ground surface, particularly at the depth of 0 to 5 meters. Therefore, our segment length is 5. Next, for depth that is 5 to 10 meters, the segment length is 5 meters. And last, we have now the depth 10 to 30, the segment length is 20 meters. So determine next and assign K per layer. For this example, the first 10 meters is normally consolidated clay. Therefore, K from 0 to 10 meters is equal to 1 minus sine of phi prime sub r, that is equal to 30 degrees. Therefore, K is 0.5. So assign to 0 to 5 and 5 to 10 meters segment. So for the remaining section under over-consolidated clay, the K for 10 to 30 meters is equal to 1 minus sine of phi prime sub r, that is 30 degrees, multiplied to the root of OCR, that is 2. Thus, K for this segment is 0.707. So assign this K to the last segment, that is 10 to 30. So for the sigma O prime, now let us consider the pressure diagram. So for our sigma O prime, so as per pressure diagram from letter B method, which is the lambda method. So for this sigma O prime, take the average vertical effective stress or overburden pressure per segment or per predetermined segment. So the average sigma O prime of 0 to 80 is equal to 40 kilopascals. For the second segment, the average of 80 and 115.95 kilopascals is 97.975 kilopascals. And for the last segment, the average of 115.95 and 279.75 is 197.85 kilopascals. Take note and assign. So assigning now our sigma O prime. So from our previous diagram, so we have for 0 to 5, that is 40, 5 to 10, 97.975, and 10 to 30, 197.85. So we have already all the parameters. Therefore, for our segment values or the components of our Q sub S. So for Q sub S, it is equal to P times delta L times K times sigma O prime times tangent of phi prime sub r in kilonewtons. So for the first segment from 0 to 5 meters, the perimeter is equal to, for circle, pi times diameter 0.4 times the segment length, which is 5 meters, times K of 0.5 times sigma O prime of 40. Then multiply that to the tangent of phi prime sub r for this problem, it is 30. Thus, the first component for QS is 72.552 kilonewtons. Next, for segment 5 to 10, the perimeter is pi times 0.4 meter times delta L of 5 times K of 0.5, then multiply it to the sigma O prime, that is 97.975, and multiply to the tangent of phi prime r, that is 30 degrees. Thus, the value of the QS for the second component is 177.707 kilonewtons. And for the last segment, that is from 10 to 30, the perimeter is pi times diameter 0.4 meter multiplied to the segment length, that is 20 meters, times K of 0.707, then times sigma O prime of 197.85. Then multiply it to the tangent of P prime R, which is 30 degrees. Thus, for the last component, it is 2030.02. Therefore, sum all components of QS, the QS is equal to 2,280.279 kilonewtons for beta method. For your assignment, please consider this problem. Okay, so that's it for the topic pile foundations under frictional resistance Q sub S in clay or for clayey soils. Take care and God bless.